In this video, I'm going to go over conservation of momentum and Newton's third law. Let's start the lesson using a gun. When you fire the gun, the bullet is shot and is acted by a force of F1. And also immediately you know that according to the Newton's third law, it will give a reaction on the rifle, F2. F2 and F1 must be equal but in opposite directions, according to action-reaction law. So F1 is equal to negative F2. So far, everything is clear, you know that. Now let's say the total time of action of the force F1 when the bullet is in the gun has already been delta t. Okay? So the force is acted on the gun, on the bullet or the gun for delta t seconds. Mathematically, I'm allowed to multiply both sides of this equation by the same delta t. So let's say F1 delta t is equal to negative F2 delta t. You remember F was delta p over delta t. In previous videos, I mentioned it a lot. So delta p, change in momentum, is going to be F times delta t. So here I see change in momentum of the bullet, and here I see change in momentum of the rifle. So delta p1 is equal to negative delta p2. So delta p of the system, what do I mean by the system? System is rifle plus the bullet, is going to be delta p1 plus negative delta p2, which is equal to 0. Because delta p1 and delta p2 have the same size, so the total change in momentum of the system is 0. What do I mean by that? Conservation of momentum. Momentum of a system is always constant if no external force acts on it. You know that the force acted on the bullet is not an external force, it's internal force. When you fire the gun, there is no external force acting on the system. So the total momentum of the system remains constant. If the system has already been at rest, now the system still is at rest. So if the external force, net force acting on the system is 0, the total momentum of the system will be the same, unchanged. This is called conservation of momentum. You see that the conservation of momentum is nothing but the Newton's third law in another language. Another example is a person who is shooting some balls out of the cart. Let's say there is no friction between the wheels and the ground. So the cart has no friction with the ground. In this way, regardless of the vertical forces acting on the system, which can cancel each other like the normal force, and also the mg, which can easily be ignored because they are not horizontal. If the boy is acting a force of F1 on this ball, the ball also will have the same reaction on the cart, F2. And you know that F2 will be equal to negative F1. This is why when you shoot the ball, actually the total displacement of the system is 0. Although it has already gained a delta P, let's say this delta P is 100 in SI. The delta P of this system also will be negative 100, same. So the total change in momentum of the system is 0, and we can say that the displacement of the center of mass of this system is 0. Let's say the center of mass of this system is here. I consider the center of mass of this system here, Cm, center of mass. The center of mass of the system is still here. Although the cart has already displaced for a few centimeters rightward, but also this ball displaced leftward. So the total displacement of the center of mass is 0. The system is not acted by any external force, so there is no change in momentum. So if the system has already been at rest, and if we consider the total momentum of the cart plus this ball to be 0, the total momentum of this system also is 0 because it's not acted by any external force. Another example is the rocket in space. Let's say this is a space rocket out of any gravity and any external force, and the engine is off. Then the astronaut decides to turn on the engine. So when they fire the system, they turn on the engine. Actually, the rocket is acted by a huge force of F1 rightward and simultaneously is acting the same force of F2 equal to negative F1 on the gas. And so the total change in momentum of the rocket plus the gas will be zero. If the rocket has already been at rest, let's say the total momentum is zero, again the system is at rest. Although the rocket accelerates rightward, but also the gas accelerates leftward, the center of mass of the rocket plus the gas won't change. So let's follow the rocket in the successive moments. You will see that there are more and more outcoming gas, and the rocket is accelerating more and more to the right, but the total displacement of the system is zero. It's interesting that if you fire the rocket in the space, even if the rocket travels for millions of kilometers, actually the displacement of the system, I mean the total displacement of the rocket and the fuel repelled out, will be zero. They cannot move because there is no external force and so no change in momentum. Let's consider this example. An astronaut of mass 90 kilogram, including his gear, is initially at rest outside a spaceship. Okay, the astronaut throws a tool of mass 1.5 kilogram at a speed of 3. So let's say it's a hammer. He will throw the hammer of 1.5 kilogram of mass leftward, at a speed of 3 meter per second, away from him. You know what happens if the astronaut is supposed to be acted by no external force. So this system will have no change in momentum. So whatever the momentum is gained by the hammer, the astronaut also will gain the same momentum. Actually, P1 minus P2 is zero. P1 is the momentum of astronaut, or let's say hammer, after throwing, and P2 the momentum of the other. So the total will be zero. This is why I can say momentum is mass times velocity. So let's say the astronaut is 90 kilogram as given. So it's for astronaut, 90 times V1 minus because if you say positive direction is to the right, so the hammer will go to negative direction. It's negative 1.5 times 3. Mass of the hammer and the velocity, 3. Is 0, so easily we can find the speed of the hammer to the left, and it's 0.05 meter per second. Thank you for watching this video. In future videos, I will teach you how to use this conservation for solving problems.